Number 3, you want me to do this? Okay, class starts. So tomorrow we have an exam, and if you like, I can go over this last exam from 2005. Would you like? Okay, so I'll take some time to go over this exam, which I'm pulling off the web, so you can pull this off the web yourself, from February 2005, so 2 years ago. Last year I was on sabbatical. So there are 5 questions. Here's the first one. What is the unit vector in the direction of this one? So do you know how to do that? Correct. So the magnitude of a vector is itself dotted with itself, take the square root. So it's 2 minus 1, 6, dotted with 2 minus 1, 6. So that's 4 plus 1 plus 36. So 41. Square root of 41. So it's 2 over the square root of 41 minus 1 over the square root of 41 and 6 over the square root of 41. So that's meant to be more or less a giveaway problem. W over the magnitude of W. Just to warm up, in case you're nervous during the exam. So don't be afraid if it seems too easy. Sometimes it is also easy. Okay, so that was the first one. Now the second one, what's the 3-1 component of the tensor B dot A? How about that one? B dot A transpose. So we're just going to write B dot A in Einstein notation. So help me out. B-I-J, E-I-E-J. K, L is so close to I usually avoid L. M, let's say. E-K, E-M. Whole thing transposed. So we'll do the dot product first. Delta J, K. J becomes K. If I'm going too fast, just say slow down. I'll go slower, okay? So J becomes K, B, I, J becomes K, A, K, M, E, I stays, E, M stays.
Switch the E, I and the E, M.
Right. B, I, K, A, K, M. We don't transpose this. We just transpose the unit vectors. And that's the final answer. And the question is, what is the 3-1 component? That's my notation for the 3-1 component. So what's the 3-1 component? M equals 3, I equals 1. Huh? Does that make sense?
Yeah.
What happens to the K?
You have to do alterate that.
Right. So it's the summation, K equals 1 to 3, M equals 3, I equals 1. So here there's an I, so that's a 1. This is still a K, this is still a K, M is 3. That's the 3-1 component. And now we can write it out, B1, 1, A1, 3. So that was K equals 1. B, A, 1, 2, 2, 3, that's K equals 2. B, A, 1, 3, 3, 3, that's K equals 3. You just have to let the technique do the work. So the technique was to write it out in Einstein notation and to do the dot product. You know, you've learned this part, J becomes K. That's doing the work of the orthonormal unit vectors. The transpose, you know to only switch the basis vectors. You don't try switching stuff in here. It can be done, but it's safer to just switch the basis vectors. You won't ever make a mistake. I could give you something really nasty and complicated, but if you only switch the basis vectors, you will get the right answer. And then a question like this about the components is a question about the basis vectors. These basis vectors are telling you, you know, which one is the 1, 1, which one is the 2, 1, 3, 1, etc. So you just put this one is 3, this one is 1. That'll give you the 3, 1 component. But if m is 3, then over here where there's an m is also 3. And if I is 1, then over here where there's an I is also 1. And any leftover repeated indices, there's a missing summation. So we're just letting the technique do the work, and then we get this. Otherwise, we have to do these matrices, and you have to go back to your linear algebra class and do them all out, and each term is going to be a 3 by 3. I mean, it's going to be sum of 3 things, right? This plus this plus this is just the 1, 1 component. This plus this plus this is the 2, 1 component. That's the same calculation as what we're doing, but you got to admit this is easier. This is a lot easier than doing this enormous array where everything is the sum of 3 and then transposing it and figuring out, okay, that's the 3, 1 on the bottom left. That's why we do it, because it's easier. Okay, it's the same as this. All right, next one. For steady shear flow, the velocity vector is given by this. Gamma dot naught is a scalar constant. What is the rate of deformation tensor for this flow? How would you approach this one?
Calculate out del V.
Right. So we need to know, the question is what is this for a given V? This is some constant. This is a variable. These are zeros. That's nice. So we need to calculate this out. And we're given the equation, del V plus del V transpose. So we have to write this out. We have to write out del V. So we've got the V. We need del V, so we go to Einstein notation. What's del V? This actually requires some practice that I recommend you do. All right? So we go back and we do d by dx p e p v s e s. It's a tensor. There are 2 basis vectors. We can put that v up into the derivative. And so it's got 9 components. Now to write that out in the matrix form, looks like this. It looks like 9 dv's, dx's. But which one's which?
So that just says you count across and the V's down.
Correct. That's correct. The v's are in the columns. So this is 1, this is 2, and this is 3. And the x's go across the rows. Okay? So this is 1, this is 2, and this is 3. How do you remember that, Carl?
I was actually wrong.
Oh, and I corrected you. So how can we remember it? You just have to remember it, I guess.
Well, it's the same as matrix notation, right?
It is for me, but I think it depends on how you think about these things. For me, I always go 1, 1, 1, 2, 1, 3. I always think about it that way. 2, 1, 2, 2, 2, 3. 3, 1, 3, 2, 3, 3. However you need to, you have to be able to do that because that shows up in the Navier-Stokes equation. So now, what is that for our vector? V. We're not done yet. What's dv1 dx1? What's v1?
Gamma x2.
What's v2?
0.
What's v3?
0.
Okay, so starting with that, everything with a v2 and a v3 is 0, right? What's dv1 dx1? You see any x1s? So what's dv1 dx1?
0.
What's dv1 dx2? Gamma dot naught. And what's dv1 dx3?
0.
0. So del v is 0, 0, 0, gamma dot naught 0, 0, 0, 0, 0. Right? That's all we're doing. What's del v plus del v transpose? Right, gamma dot naught also in the 1, 2 position, because when we transpose, we get a gamma dot naught here and everywhere is 0, and when we add the two together, we get them in both positions. So this is 0, gamma dot naught 0, gamma dot naught 0, 0, 0, 0, 0. I think that was the answer. Question was, what is gamma dot, the tensor in this flow? And there's the answer. We're going to use this tensor a lot. This is the shear, rate of deformation tensor for steady shear flow. So for instance, for a Newtonian fluid, we're going to do this today maybe. For a Newtonian fluid, the stress is equal to minus mu gamma dot the tensor. So we've now calculated that. So for steady shear flow, the stress would be 0 minus mu gamma dot naught 0 minus mu gamma dot naught 0. That's the stress tensor in steady shear for a Newtonian fluid. It's a constant. It's a constant, and minus the stress over the shear rate is equal to the viscosity, which is most people's definition of viscosity. And that's where it comes from. The third one, what is del dot v in Cartesian coordinates? The fourth one. Now, to me, this is seeming like a very easy test. What do you think? Not too bad, right? What is del dot v in Cartesian coordinates?
You just want to do del dot v and find out, do that through Einstein and then find out, because that's all going to be a scalar at the end.
And then carry out the summation. Right. So d by dxi dot vp ep delta ip, I becomes p, dvp dxp. We've seen that before, right? When we did the homework and we did putting things in the, we did the problem with show that this identity is equal to, the left side equals the right side. This was one of the terms that was there. This dvp dxp, where they're both the same and it's a scalar, it shows up all the time. It's the trace of gamma dot. If we go back here, Look at this. The trace. dv1 dx1 dv plus dv2 dx2 plus dv3 dx2. The sum of the diagonal elements. It's the trace of del v. That's not so essential for this problem, but I just thought I'd mention it. So there's a duplicated index, so that means there's a missing summation, p equal 1 to 3, dvp dxp, which means it's dv1 dx1 plus, dv2 dx2 plus, dv3 dx3. Done.
But since you say like Cartesian coordinates, when you
Cartesian means x, y, z,
yeah.
after Descartes. I wouldn't ask you it for cylindrical, because I'm not asking you to memorize those. But it wouldn't be that hard. It's just
Yeah.
dvr dr, 1 over r dv theta d theta, and dvz dz. That 1 over r part's the only tricky part. But I only know that from using it over and over again in my life, and I don't expect you to memorize that. And then the last problem, 30 points. That's what it looks like. Cartesian. A steady pressure-driven flow of an incompressible Newtonian fluid is created between two very wide parallel plates. The pressure at position 0 is P naught, at position L is PL. Please answer the following questions. You must show your work. What is the differential equation for velocity and pressure? What are the boundary conditions? What is the steady-state velocity profile? What is the steady-state pressure profile? The only reason this is written out as 4 questions is so that I can grade it easier. Okay? It's basically solved flow, pressure-driven flow in a slit. Okay? So how do we do it? We're flying without a net. No table given because it's Cartesian. Okay, what do we do?
Well, since you since we've done like problems like this before, like it's fair game if you remember right
Yes.
away. Oh, okay.
What do you remember?
Like the equations. I mean, I thought that comment, but I might tomorrow.
Which one?
Well, you have the equation of state and then the
Continuity, you mean?
continuity.
Continuity equation and equation of motion. These you don't have to memorize. They're on the top of the exam paper,
Okay.
right there. This is the general continuity equation. Okay? So for constant density, this time term goes out, and you can take this guy out and cancel him out, and it becomes del dot V. And there's the Navier-Stokes, both given.
So where do you get your V there in the continuity equation?
We can solve for V. Is that
Yeah,
the question?
But like is the rho dt and then just have
V dot del V. This is the V dt.
no, yeah, I'm talking about like the continuity equation. That's what you
This one?
Yeah, because over there in your exam, right? You don't have a V there anymore.
If we go back to the other continuity question, it's no V because it's density. The rho dt equals minus del dot rho V.
Oh, that's a V. I'm sorry.
So this is steady state,
Yeah.
and then this is constant, so it comes out, and we get minus rho del dot V. And that's because steady state equal to 0, we get minus rho del dot V equals 0. Divide through by rho, divide through by minus 1.
Yeah.
Del dot V equals 0.
It looked like a G from here.
Look like a G. Okay, it's small.
I think so.
Yep, it's small.
Closer. Yeah.
Up close and personal on the Navier-Stokes equation. Now what?
Well, we know what delta V is from just doing it.
What is it?
It's dx1, dv1 dx1 plus dx2 dv2. I mean,
I gotcha.
dv2 dx2, dv3 dx3.
All right.
Steady state, so we cancel the time derivative.
Steady state.
It's unidirectional flow, so all the second part goes out as well.
Right.
Expand del P.
Okay. D by dxi p. D by dxi pei. dp dx. dp dx2. dp dx3. Next.
And
Do
next
gravity.
bit.
Gravity, we could do gravity next. Rho g. What's the g vector?
So in the -2 direction.
Right, negative g, and then the rest is 0. So that's done.
Calculate del dot del.
Right, we need del dot del v here. So we've got mu del squared v, which is mu del dot del v. That you had to know. You had to know that del squared v meant del dot del v. And then the rest is Einstein. So it's mu d by dx p ep. I'm just, every time I see a del, I'm writing this. If I see the same thing twice in the same expression, I use new subscripts. That's the other rule. So I'm seeing del again. I leave the dot where it is. I get new subscripts. I pick j. And v, I pick new subscripts. Then I'm just following the usual rules. The two unit vectors that are nearby are the ones that get dotted. It becomes delta pj. P becomes j. And I get mu d by dxj, d by dxj, vk, ek. So to write that in vector notation, I need to know what the one component is. So what's the one component of that?
One component is the v1, and then you change your x from 1 to 3.
Right. So it's dv1 dx1
Square
plus dv1. I'm always in the, when k is 1, this subscript k is 1. So for all three terms, summation j equals 1 to 3, x2 squared, plus d squared v1 dx3 squared. So that's the one component of del squared v. Right? What's the two component?
Same thing, except change the v.
Right, same thing except change the v to 2. So in order to prevent myself from doing any mistake, because you know how your brain works when it's 1, 2, 3, 1, 2, 3, 1, 2, 3, I usually just write dv dx plus dv dx plus dv dx. Now I know they're all second derivatives, so I put that in second. And then these go 1, 2, 3. Okay? Can't make a mistake if you do it like that. And then these are all twos. So I do that again. Second derivative v with respect to x squared plus second derivative of v with respect to x squared plus second derivative of v with respect to x squared. These are all threes. These go 1, 2, 3.
Just
There's
cancel
no
everything.
V2 and
There's no flow in the,
second and third.
right? There's no V2s. There's no V3s. If you know that ahead of time, you can write 0, 0 for me here. If you know that, that's okay. Get it right. I'm fine with that. If you're not perfectly confident, then do it from scratch. I'm going to time the test so that I can do it in about half the time, I guess, maybe a little less. Okay? Which means I have to do all this too, but you know I'm pretty fast at this. Okay? I'm not going to race through it in my timing, but I don't have to think that hard about it. Okay? What else?
Just the middle term is the only one that stays.
And why do the other two go away?
goes to
Stay, stay.
Right? This one comes out of the continuity equation, the del dot v. Right? dv1 dx1. And this one?
It's just
wide plates.
Wide
Upper
plates.
wide
Right, wide plates. If we look over at the problem, the 3 direction is this width direction. And we're saying that in any cross section, whether I draw the cross section here, here, or in the back, I think the flow is going to be the same. It's going to look like this, or it's going to look like this, or it's going to look like this, in any position of x3. So it's not depending on x3. Wide plates. And so we have just this term. And if we put them all together, we get 0 equals minus dp dx1 minus dp dx2 minus dp dx3 plus mu del squared v1 dx2 squared, 0, 0, plus 0 minus rho g, 0. So my advice has always been to leave pressure alone because the Navier-Stokes equations will tell you what pressure is. And so here it is telling me, right? The pressure variation in the 3 direction is 0. The pressure variation in the 2 direction is hydrostatic. It's rho GH. That's what this is saying. It's just the pressure change due to gravity. And the pressure change in the 1 direction depends on the flow. And that's the one we have to solve. So we get dp dx3 equals 0, dp dx2 equals minus rho g, and dp dx2 equals mu dv1 dx2 squared. So So the problem asked, what is the differential equation for velocity and the pressure? So we've got it. Okay? These are the differential equations for velocity and pressure. That's part A. What are the boundary conditions on velocity and pressure?
Velocity is 0 at x2 equals 0 and x2 equals 2h.
X2 equals
Okay, now look at my
Oh.
coordinate system.
plus or minus h.
Right. V1 is 0 at plus and minus h. That's two boundary conditions. That's sufficient. But there's an alternative boundary condition.
The derivative with respect to x2 of the velocity profile is 0 at 0.
Right. At x2 equals 0, the velocity must go through a maximum. Don't do this. V1 equal V max. The correct boundary condition is that what Juan said, that the derivative is 0 at the maximum. This one we can use. V max we don't know until we finish the problem. When we finish the problem, we can calculate V max from this, from setting the velocity derivative equal to 0. Okay, so this is part A, full credit. This is part B, full credit. Question?
You have to put pressure boundary conditions too.
Yeah, you're right. I haven't finished. You're right.
But they're-
Okay, what are my pressure boundary conditions?
I mean, they're given right there.
They're given right on the screen there. At x1 equals 0, p equals p1. At x2 equals 0, p equals p2. What about this?
Neglect.
Yeah, this has been neglected. If these are the boundary conditions on pressure, then in fact the gravity has been neglected. But we'd actually, we could try. Well, I've got an x2 here instead of an x1. We could try continuing with it and see if it gives us trouble. It will. If we don't neglect gravity, there'll be trouble. This is what I expected, though. In my problem, I should have said to neglect gravity. I don't usually put trouble in on a test like that, but in this case, it looks like I did. All right, so this is what I expected. And then, what is the steady state pressure profile? What is the steady state velocity profile? Okay, so if we don't neglect gravity, then we have pressure is a function of x1 and x2. And its partial derivative with respect to x1 has to be equal to mu partial derivative v1 squared with respect to x2 squared. So to solve this equation, the usual way we solve Poiseuille flow is by separation of variables. Put everything that's a function of x1 on the left, everything that's a function of x2 on the right. And that's where this is giving us trouble. Okay, we're not actually able to separate the variables unless we neglect gravity. If we neglect gravity, then it's not a function of x2 anymore. And then we can solve it. This becomes dp dx1 equals mu. Actually, we usually put the mu on this side. No, we don't. No, we don't. Leave it where it is. Second derivative v1 with respect to x2. This is only a function of x2. This is only a function of x1. This is exactly the same way that Poiseuille flow in a tube is solved for, which is why I sort of expect you to be a little bit familiar with it. And so if they're both functions of independent variables, they must be equal to the same constant, which I usually call lambda. So we have two differential equations to solve. dp dx1 equals lambda. And second partial v1 with respect to x2 equals lambda. Is that fair enough? Okay, so now we can solve this with the given boundary conditions, and it becomes ... missing steps. P equals P minus P over L x1 plus P naught. This is P naught, that's PL. That's the final answer. Missing steps there. This one integrates twice to become a parabola. Integrate it once, dv1 dx2 equals lambda x2 plus a constant. Integrate it again. v1 is equal to lambda x2 squared over 2 plus c1 x2 plus c2. So you see, the danger in forgetting your integration constant is that you completely miss a one whole term. So when you do an integration like this, don't forget your integration constant.
Should you apply your boundary condition before you do the second integration to solve for C1 though?
If you have one that's a boundary condition on V1, which we do in this case if we choose that one. So yes, you can. If you want, you can apply the boundary condition, which is that x2 equals 0. The derivative is 0, which means C1 is 0. And the second boundary condition is at the wall. We can pick the top or the bottom. x2 equals h, v1 equals 0, v1 equals lambda h squared over 2 plus 0 because c1 is 0 plus c2 has to equal 0. So therefore, C2 equals minus lambda h squared over 2. And lambda we get from here. dp dx is lambda. And in the course of this ... where I left out some steps, we solved for lambda. Lambda is equal to PL minus P naught over L. Some more algebraic steps and we're done. What? What happened to mu? In this problem? Oh, yeah, it's here. Good point. Thank you. We lost it. That's what happened to it. So that was the exam 2 years ago. So it was a flow problem, which takes the most time. It was an incredibly easy one on magnitude of a vector, and 3 that had something to do with Einstein notation. And then because it was a Cartesian problem, there was a bit of Einstein notation in doing the flow problem as well. Any other questions? Is that helpful? So I would recommend looking over the flow problems because those are the hardest ones. If you're not comfortable with Einstein notation, I would practice that a little bit. There are examples in the book, and there's the homework and the homework solution as well. It's just sort of a skill development. The Einstein notation is really just a bunch of rules. How to write the del, how to write a v, how to write a tensor, what to do for a dot product, what to do for the scalar product. How do you do this one? A double dot B. Right. So if you can do that, that one's good. We've already done this one, del squared. That's del dot del. There's magnitude of a tensor, but if I accidentally ask you to do that, I wouldn't mind telling you the definition. A double dot A over 2, the whole thing square root. I'll tell you that. So if I do make a mistake on the exam and ask you something that you need a definition, I'll tell you it. The purpose of having a closed book test is to have you spend your time both in preparation and in doing the test, in learning how to do the Einstein notation for real, and in learning how to do the flow problems for real. It's not to make you memorize things. So my intention is not to make you memorize things, except how to do an Einstein notation and how to do these flow problems. Okay? The flow problem I give you cannot be a super difficult one. It can't be a really, really difficult one. They just take too long. But it will be a complete flow problem. So if you want, you could go through and try to figure out which ones it could be, because it's really a very short list. And if you know them all, that's sufficient for my purposes. The hardest one to solve in terms of integration is probably this one, because you have to remember this trick of separating the pressure and the velocity. If there's no pressure, then that term doesn't even enter, and it's even easier. Okay, so let me go back to the new material, and we'll finish up the test tomorrow night. So when we finished our last lecture, this is what I said. We had learned about the stress tensor. We had learned that symmetric. We had learned that when we put it in the standard flows, it's very simplified. These are our two standard flows, shear and elongation, all three types of elongation. And the question, what's next, is a valid one. And this is what I said at the very end of class on Friday, that what are we going to do with these standard flows? And I said that what we're going to do is produce standardized tests, kind of in the spirit of an ASTM standard test, but a little bit more rigorous, because we've picked flows that are very standardized. They have some very few quantities that we have to measure. We just, in shear, have to measure one shear stress and two normal stress differences. And in elongation, two stress differences. And what we can do with these is develop constitutive equations or use them to compare various materials. Now, the tests that we're picking are in contrast to just sort of, in some sense, the gee whiz experiments that were in the movie. So these are some stills from the movie we saw. And I don't know, I'll try to remind you what you saw. We saw this experiment where he showed something that had a yield stress. He put a very viscous material in a container. He put a weight on it. It did not flow. He put a much bigger weight on it, and it started to flow. So we need a test that's sort of like that, that will tell us what's going on with a fluid that flows sometimes and doesn't flow other times, because Newtonian fluids don't do that. This is a non-Newtonian effect. So we need a test that will allow us to quantify that. And the test that allows us to do that is steady shearing test, but also startup of steady shearing. He also showed us this gee whiz test where he took a piece of silly putty and set it for a long time and it puddled out. This is called a creep test, actually. This is putting a constant force, a constant stress, this is gravitational force, putting that force on this for a long period of time. And you're going to see that one of our standard tests, one of our experiments, our material functions, is going to be imposition of a constant stress, not constant rate. Usually we're going to impose a constant rate, but this test is going to be imposition of a constant stress. He also did bouncing of a ball. We're not going to have a test that has anything to do with that. This is an elasticity measure, but it's kind of an impulse measurement. And that's happening too fast for us, so we're actually not going to see one like that. This one was kind of interesting. He put a sample in a cup and bob. So there's a bob on the inside and this outside thing I would call the cup. And there's a sample in the gap, so it's an annular flow. And he spun that around and he saw that he had some sort of a reversal, flow reversal. He spun it around and it came back in the original flow direction. He was trying to demonstrate to you flow memory. And we're going to need some tests or another that elucidate flow memory. It's going to be, the one we pick is going to be similar to this, but it's actually going to be more related to the other demo he did. He did this really neat one where he used the same geometry, cup and bob, and he really did a very nice job with this hanging the pen and moving the pen. And he saw that for a Newtonian fluid, he got a straight line, and then when it disengaged, a flat line. And for a non-Newtonian fluid, he got a non-straight line, and then the flow reversed direction. So this was a way of quantifying flow reversal. He did this by having this weight over on the side. So once again, gravity is driving the flow. So this is another constant stress test. This is called creep. This is creep at constant stress. At steady state, it's a steady shear flow. It's in this flow as well, it's a steady shear flow, but there's an interesting transient. And I'm going to show you pictures of data that are taken in this kind of a flow. He also showed you this, two burettes filled with a non-Newtonian and a Newtonian fluid. And for the Newtonian fluid, the doubling the pressure head doubled the output, and when he put the non-Newtonian fluid in and he doubled the pressure head, it did not double the output. So this is flow in a tube. We use that also for polymers. We use it as capillary flow, but we usually drive it, instead of using gravity, we drive it with some kind of a pressure to drive the flow out. So we will see flow in a tube as a way of measuring. What else? Here he was trying to demonstrate these normal stresses that we've now talked about a little bit, the N1 and N2. Here he has fluid in a gap turning around. He's measuring the normal pressure by using this hydrostatic measuring device. And he's saying that for a Newtonian fluid, the pressure in the center is lower than the pressure on the outside. This is like the calculation we did on Friday, where we saw that the pressure would be low in the center and high on the outside, so we expect that upward tilt to the pressure profile. And then here he saw experimentally the first normal stress difference. The pressure was higher in the center than it was on the outside. This is rod climbing, and in fact, this bubble that you see there, that was goop climbing the rod. Okay, but in addition to just stuff climbing the rod, he actually measured right there where his arrow is that the pressure was higher on the inside than on the outside. So you can, in a Couette flow, measure a normal stress difference, but you have to do it the way he did. You need a pressure transducer on the outside. And in practice, we don't do that. In practice, we use the cone plate or parallel plate, which is what he's got going here. Maybe when you first saw this, you didn't know what the heck was going on. Here he's got two parallel plates, and then he's put these tubes on the top as pressure measuring devices. When he puts the fluid between the two parallel plates and turns the bottom one, okay, it's going around and around. I can't turn my hand around and around, but around and around on the bottom, okay, it's a shear flow in that gap, and he's using the capillary tubes as a pressure measurement. When it's a Newtonian fluid, again, he gets that dip in the center that is an inertial effect. When he puts a non-Newtonian fluid, there's a high pressure, a stress pi 1,1, or excuse me, pi 2,2 in the center, and less of a normal stress towards the edges. This is how we measure normal stress differences. We measure the total force on the upper surface, which means we have to relate that total force to the distribution of forces. A little bit complicated. We'll leave that to the last chapter. Notice this bottom one. Look at how big those forces become after he turns this thing for a really long time. So these are the phenomena that we're trying to quantify, and this is how we'll do it. We'll choose one of these two flows. We're going to choose exactly how to run the boundaries by choosing sigma dot and epsilon dot. We're going to measure these stress quantities, and then we're off and running. So this is where I'll start on Wednesday after the exam, start talking about these various ASTM-like tests that we actually use in rheology. All right, so I'll see you tomorrow at 6 for the exam.